Hi, I'm Lin Clark, and I make code cartoons. And I also work on developer technologies at Mozilla. So if you aren't familiar with our team, we work on the Rust core language and WebAssembly and the Rust to WebAssembly toolchain. And if you aren't familiar with WebAssembly, it started as a way to run programming languages other than JavaScript on the web. So languages like Rust and C++ and C as well. But lately, our team has been pioneering a lot of the work on a different application of WebAssembly. This is WebAssembly outside the browser use cases. So I want to set the stage a little bit here and explain a little bit about what that WebAssembly outside the browser means. So with WebAssembly outside of the browser, we're taking WebAssembly beyond just interoperability with the web platform and on to interoperability with all of the things. So for example, how you could run a WebAssembly module using rich APIs with high-level types like strings and objects when running your code in Python or Ruby or PHP, scripting languages that are running in their own runtimes. And then turn around and take the very same module and use it to talk directly to the host or the operating system using those same high-level types, even though the types that are used on the operating system are different than the types in something like the Python runtime. And then use those same APIs, those same high-level types, when talking to a WebAssembly module written in a different source language that has different types. So for example, having a WebAssembly module written in Rust talking to one written in Go. Now, why would you want to do this? Why would you want to use it as a WebAssembly module in all of these places? Okay. Why would you want to use it as a WebAssembly module in all of these places? A few reasons. If your app is in a scripting language like Python, then WebAssembly could be much faster. You could get near native performance without the hassle of compiling a native extension. If your app is in a low-level language like C++, then WebAssembly can give you lightweight sandboxing. The module can't access memory or resources unless they've been given directly to it. So this can help make reusing code a lot more secure. And for both scripting languages and low-level languages, being able to reuse code from any language ecosystem without having to rewrite it in your language can help you work faster and also make your maintenance costs a lot less. If there were a way to run the same WebAssembly module across all of these different environments, that would unlock a lot of wins. So that's something that we've been working on with something called the interface types proposal. And I wrote a little bit more about this in a blog post that's on the Hacks blog, Mozilla's Hacks blog, a few weeks ago. So if you want to dive into the details, you can read that post. But right now, I just want to show it to you in action. So now I'm going to do a demo, but I have to say, I have a healthy fear of the demo gods, so I've actually pre-recorded everything here. So now we need a scenario. And the scenario I'm going to use is, let's say that we want to build a tool, a build tool, for taking markdown files and turning them into static websites. So for that, I need a markdown parser. And also to show this off, I need a module that actually uses interface types. So we're going to go ahead and create one. So I'll find a markdown parser written in a language that can be compiled to WebAssembly, so something like Rust. Now, since I'm not the author of this module, I can't add the interface types directly to the module, so I'm going to wrap it. But if you were actually coding your own module, you could just do this in your module's code. So let's see. So I'll create a render function which uses string types, and I'll add a WASM bindgen annotation above it. This does all of the magic. It knows the various Rust string types, and it knows that they should map to WebAssembly's high-level string type. That's not part of the WebAssembly spec, that's part of the interface types proposal. And then I'm going to compile it. And I'll do this using a tool called WASM-Pack. And I'll use the WASM interface types flag, because this is still an experimental feature. We need to do this to let the compiler know that we're using this feature. And this gives us the single WASM file to use in all of these different environments. Now for our first environment, let's go with pure WebAssembly. For this, we need a WebAssembly runtime that comes without JavaScript, so one that can easily be run outside of the browser. And that's what our WASM+ runtime is. So we'll download WASM+ from wasmtime.dev. And then we can run this module and pass in the markdown string. And you see the WebAssembly module took the markdown string and returned the HTML string. Even though the runtime doesn't know anything about how Rust strings work, they were able to communicate with each other using this high-level type. So that was easy and straightforward. But what about Python? Can we use this markdown parser there? Yes, and we may want to for speed. To do this, we download the WASM+ extension. Now, this makes it possible for Python modules to call WebAssembly functions. Now all I need to do is import the extension, and then I can import the markdown module, and then I can call the render function. And now we run this. And again, it works. The types are different this time. We're passing in Python values, but it still just works. Because of the magic of interface types, the same file runs in the same way. We can also use the same WebAssembly module in Rust. Now, one reason you'd want to use it here is for that lightweight sandboxing that I was talking about before. That isolates this third-party module away from the rest of your application. So let's talk about how this works. We add WASM+ Rust as a dependency, and this does the same thing that the Python extension did before. It gives us something that we can run WebAssembly in. And then in the main file, we add the WASM+ Rust macro and a trait and a render method. But we aren't going to add an implementation of this render method. That's actually what the WebAssembly module is. Instead, what this tool does is it just wires this up for us so that Rust knows that the implementation is in the WebAssembly module. And it also adds other methods on that trait like load file. So load file means that we can instantiate this WebAssembly module in our code. And then we can call render. And something that's important to note here, the result is strongly typed. It can be used exactly the same way as a natively compiled version of this same functionality. So now let's use Cargo to build and run it. Again, it just works, except with a different environment using different types. Now, this might not seem impressive because we compiled the original module from Rust. But it would work just as seamlessly if the WASM module were compiled from C++ or Go, as long as that module were using interface types. Where else can we make this work? Well, I don't have enough time to show you, but this also already works in Node and on the web through WASM bindgen. So there's the same module, compiled to WebAssembly and running in 5 completely different languages and runtimes. And those are just a few examples. There's no reason why this can't be supported in a whole bunch more language runtimes. And beyond that, there's no reason why this can't work for talking directly to operating systems. And this is where we get to what I really came to talk about. So, would we want to have WebAssembly modules talking directly to the operating system? Well, it turns out the answer to this question is yes. As we figured out this spring when we announced the standardization of a new system interface, WASI, for doing just that. And there's been a huge uptick in interest since then, with people like the co-founder of Docker, Solomon Hykes, saying, if this tech had been around 10 years ago, they wouldn't have needed to create Docker. So let's dig into this more. Why would you want to have WebAssembly modules talking directly to the operating system? Well, I already talked about a couple of reasons. There's the portability, which I demonstrated, with the same module running across all of these different environments. And I'll be talking about that more throughout the talk. And I'll also be talking more about the security, that lightweight sandboxing that I mentioned before. So WebAssembly is portable and secure. And we'll talk about why these two things are essential in the rest of the talk. But I also mentioned the speed. And that's another big reason why you'd want to use WebAssembly. WebAssembly is fast. If you want to run code in a safe, portable way, it would be hard to find anything faster. It gives you the ability to run code at near native speeds. And it's not just that the code runs fast. WebAssembly code can also give you fast startup times. And WebAssembly VMs can start up more quickly than other VMs, like JavaScript VMs. So for example, Fastly is using WebAssembly to handle requests for their serverless platform. And they do this by spinning up a new virtual machine instance on every single request, which gives them a lot of security. They can instantiate WebAssembly modules in under 60 microseconds. Now for comparison, if you're instantiating a JS module in a runtime like V8, it takes about 5 milliseconds. WebAssembly is also scalable. It takes a lot less memory to run a WebAssembly VM than it does a JavaScript VM. Now, I mentioned Fastly before. Their WebAssembly runtime only requires a few kilobytes of memory overhead versus tens of megabytes with something like V8. So this means that they can fit tens of thousands of simultaneously running programs in the same process, as opposed to hundreds with V8. So that's why you would want to run WebAssembly outside of the browser. Now let's look at who, or what. What exactly is WASI? When I was introducing WebAssembly, I talked about how it was an assembly language for a conceptual machine, not for an actual physical machine. This is why it can run across a bunch of different machine architectures. WebAssembly is very close to the assembly language that most machines use. So the runtime only needs to do a small translation from WebAssembly to the actual assembly language specific to the machine that the code is actually running on. It goes from the assembly language for the conceptual machine to the assembly language for the actual machine. Just as WebAssembly is an assembly language for a conceptual machine, WebAssembly needs a system interface for conceptual operating system, not for any single operating system. And this way it can be run across a bunch of different kinds of operating systems. And this is what WASI is, the system interface for the WebAssembly platform. Now, who's working on this? WASI is being standardized by the WebAssembly community group. We've chartered a subgroup to work on it, and you can find out more in the WebAssembly/WASI repo. So if you want to get involved in this, you have a few options. You can join the CG and work on standardization, or you can also start contributing to one of the implementations, such as WASM+, the WebAssembly runtime that we're working on at Mozilla. Or, if you have an existing project that can use WASI, feel free to get in touch, and we can talk about that. So for example, we've been talking with the Node folks about how they could possibly use WASI to make native module development a lot easier and safer. So now that we've covered all of that, let's talk about WASI in more depth. Now, some of you may already know how operating systems work, but I like to cover things from the ground up to make sure that we're all on the same page. So I'm going to give you a few operating system basics. Many people talk about languages like C giving you direct access to system resources, but that's not quite true. These languages don't have direct access to do things like open or create files on most systems. Why not? Because these system resources, such as files and memory and network connections, are too important for the security and the stability of your code. If one program unintentionally messes up the resources of another, then it could crash the program. And even worse, if a program or user intentionally messes with the resources of another, it could steal sensitive data. So we need a way to control which programs and which users can access which resources. Now, people figured this out pretty early on, and they came up with a way to provide this control, which is protection ring security. With protection ring security, the operating system basically puts a protective barrier around the system's resources, and this is the kernel. The kernel is the only thing that gets to talk to that gets to do things like creating a new file or opening a network connection. The user's programs run outside of this kernel in something called user mode. If a program wants to do anything like open a file, it has to ask the kernel to do it for it. This is where the concept of the system call comes in. When a program needs to ask the kernel to do one of these things, it asks using a system call. So this gives the kernel a chance to figure out which user is actually asking. And then it can see if that user has access to the file before it opens it. On most devices, this is the only way that your code can access the system's resources through these system calls. And it's the operating system that makes these system calls available. But if each operating system has its own system calls, wouldn't you need a different version of the code for each operating system? Well, fortunately, you don't. How is this problem solved? Abstraction. Most languages provide a standard library. While coding, the programmer doesn't need to know what system they are targeting. They just use the interface. Then when compiling, your toolchain picks which implementation of the interface to use based on which system you're targeting. This implementation uses functions from the operating system's API, so functions that are specific to the system. And this is where that system interface comes in. So for example, putC is the interface. When it's being compiled for a Windows machine, it can use the Windows API to interact with the machine in the implementation. And if it's being compiled for Mac or Linux, it will use POSIX instead. This poses a problem for WebAssembly, though. With WebAssembly, you don't know what kind of operating system you're targeting, even when you're compiling. So you can't use any single operating system's system interface inside of the WebAssembly implementation of the standard library. As I mentioned before, this is why WebAssembly needs that conceptual operating system, not the one single operating system. But there are already runtimes that can run WebAssembly outside of the browser, even without having this system interface in place. How do they do it? Well, let's take a look. The first tool for producing WebAssembly was Emscripten. It emulates a particular operating system's system interface, POSIX, but for the web. So this means that the programmer can use functions from the C standard library, libc, in their code. Now to do this, Emscripten created their own version, their own implementation of libc for the web platform. This implementation was split in two. So part of it was compiled into the WebAssembly module, and the other part was implemented in JS glue code that WebAssembly module talked to. And then the JS glue code would call into the browser, and the browser would call into the operating system. Most of the early WebAssembly code was compiled from Emscripten. So when people started wanting to run WebAssembly without a browser, they started by making Emscripten compiled code run. So these runtimes that were running this code, they needed to create their own implementations for all of these functions that would have been in the JS glue code. There's a problem here, though. The interface provided by this JS glue code wasn't designed to be a standard or even a public-facing interface at all, because that wasn't the problem it was solving. So for example, a function that would be called something like read in an API that was designed to be a public interface. For that, the JS glue code instead used _system3 with the parameters which and var args. So that first parameter, which, is an integer, which is always the same as the number that's in the function name. So 3 in this case. The second parameter, var args, is the arguments to use. And it's called var args because you can have a variable number of them. But WebAssembly doesn't actually provide a way to pass in a variable number of arguments to a function. So instead, the arguments are passed in via linear memory, so basically via the heap. Now this isn't type safe, and it's also slower than it would be if the arguments could be passed in using registers. Now that was fine for Emscripten running in the browser. But now runtimes are treating this as a de facto standard, implementing their own versions of this JS glue code. So they're emulating an internal detail of an emulation layer of POSIX. This means that they are re-implementing choices like passing arguments in as heap values that made sense based on Emscripten's constraints, even though these constraints don't apply in their environments. If we're going to build a WebAssembly ecosystem that lasts for decades, we need solid foundations. This means our de facto standard can't be an emulation of an emulation. But what principles should we apply? This is where we come back to these two important principles that I talked about before, and which are baked into WebAssembly: portability and security. We need to maintain these key principles as we move to outside the browser use cases. As it is, POSIX and Unix's access control approach to security don't quite get us there. So let's look at where they fall short. We'll start with portability. POSIX provides source code portability. That's what the P in POSIX is for, portable. You can compile the same source code with different versions of libc to target different systems. But WebAssembly needs to go a step beyond this. We need to be able to compile once and run across a whole bunch of different machines. So we need portable binaries. This kind of portability makes it much easier to distribute code to users. Now let's look at security. When a line of code asks the operating system to do some input or output, the operating system needs to determine if it's safe to do what the code asks. Operating systems typically handle this with access control that's based on ownership and groups. So for example, the program might ask the operating system to open a file. And they'll ask on behalf of the user who started the program. That user has a certain set of files that they have access to, either because they own them or because they're part of a group that has access. So when the user starts the program runs on behalf of that user. And if the user has access to the file, then the program has access to that file. This protects users from each other. And that made a lot of sense when early operating systems were developed. Systems were often multi-user, and administrators controlled what software was being installed. So the biggest threat you had was that other users would take a peek at your files. That's changed, though. Systems now are usually single user, but they're running code that pulls in lots of other third-party code of unknown trustworthiness. So now the biggest threat is that the code that you yourself are running is going to turn against you. So for example, let's say that you had a library that you're using in your application, and it gets a new maintainer, as often happens in open source. That maintainer might have your best interests at heart, or they might be one of the bad guys. And if they have access to do anything on your system, for example, open any of your files and send them over the network, then their code can do a lot of damage. This is why using third-party libraries that can talk directly to the system can be so dangerous. WebAssembly's way of doing security is different. So WebAssembly is sandbox by default. This means that code can't talk directly to the operating system. But then how does it do anything with system resources? Well, the host, which may be the browser or it may be a runtime like WASM time, puts functions into that sandbox that the code can use. So this means that the program can limit what the runtime can limit what a program can do on a program-by-program basis. It doesn't just let the program act on behalf of the user, calling any system calls with all of the user's permissions. Now, just having the mechanism for sandboxing doesn't make a system secure in and of itself. A host can still choose to put all of those syscalls into the sandbox, in which case we're no better off than we were before. But it at least gives hosts the option of creating a more secure system. In any system interface that we design, we need to uphold these two principles. Portability makes it easier to develop and distribute software, and providing the tools for hosts to secure themselves or their users is an absolute must. Now, given those two key principles, what should the design of the WebAssembly system interface look like? Well, that's what we're figuring out through the standardization process. But we did start it with a proposal. And that is to create a modular set of standard interfaces and start with standardizing the most fundamental ones. So what will be in these most fundamental WASI core modules? Well, in our first proposal, we said that there would be this WASI core module that would contain the basics that all programs need. Now, this has changed a little bit. We've actually whittled that down considerably. I'll get to that in a moment. But fundamentally, the early WASI modules will cover much of the same ground as POSIX, including things such as files, network connections, clocks, and random numbers. And WASI will take a very similar approach to POSIX for many of these things. So for example, we'll use POSIX's file-oriented approach, where you have things like open, close, read, and write, and the rest of the system calls are built as augmentations on top of those. But WASI core, these early WASI modules, won't cover everything that POSIX does. So for example, the process concept doesn't really map very easily onto WebAssembly. And beyond that, it doesn't make sense to say that every WebAssembly engine needs to support process operations like fork. But we also want to make it possible to standardize fork. This is where the modular approach comes in. This way we can get good standardization coverage while still allowing niche platforms to use only the parts of WASI that make sense for them. And we're actually making it even more modular than we talked about in the blog post. Now the system calls for each of these things, so random numbers, clocks, file system, they'll all be broken out into their own module, and WASI core will just be the mechanism for loading these modules and a few other infrastructure things. So this way your runtime can really pick and choose what it wants to use. So an IoT device without a file system could implement the random number and clock syscalls without having to worry about the file system syscalls. Now, how will module developers use WASI? Languages like Rust will use WASI core and these other WASI modules directly in their standard libraries. So for example, Rust's open is implemented by calling WASI path open when it's compiled to WebAssembly. This means that the module developer doesn't have to know any WASI syscalls. They just use the standard library, and it gets compiled in for them. So for C and C++, we've created a WASI sysroot that implements libc in terms of these WASI functions. And we expect compilers like Clang to be able to use this, and complete toolchains like Rust and Emscripten to use WASI as part of their system implementations. And Rust actually already does have this support. How does the compiled code then actually call these WASI functions? Well, the runtime that's running the code passes the WASI core functions in as imports. This gives us portability because each host can have their own implementation of WASI core that's specifically written for their platform. So from runtimes like WASM to Node or even the browser. And it also gives us sandboxing. But because the host can choose which WASI core functions to pass in, so which system calls to allow on a program-by-program basis. And this preserves that security. But WASI actually gives us a way to push this security even further. It brings in more concepts from capabilities-based security. So traditionally, if code needs to open a file, it calls open with a string, which is the path name of the file it wants to open. And then the operating system does a check to see if the code actually has permission based on the user who's running it to run the file with that this string identifies. With WASI, if you're calling a function that needs access to a file, you actually have to pass in a file descriptor for that. This is basically an object and has permissions attached to it. So this could be a file descriptor for the file itself or for a directory that contains that file. This way, you can't have code that randomly asks to open etc password. Instead, the code can only operate on the directories that are directly passed into it. So this makes it possible to safely give sandboxed code more access to different system calls because what those system calls can do can be limited. And this happens on a module-by-module basis. By default, a module doesn't have any access to file descriptors. But if code in one module has a file descriptor, it can choose to pass that file descriptor to functions it calls in other modules, or it can create more limited versions of the file descriptor to pass in to other functions. So the runtime passes the file descriptors that the application is allowed to use in at the top level, and then that gets propagated down through the rest of the code on an as-needed basis. This gets WebAssembly closer to the principle of least authority, where a module can only access the resources that it really needs in order to do its job. Now these concepts, they come from capability-oriented systems like Cloud API and Capsicum. One problem with capability-oriented systems is that it's often hard to port code to them. But we think that this problem can be solved. If code already uses system calls, like openat with relative file paths, compiling the code will just work. If code uses open and migrating to the open at style is too much upfront investment, WASI can actually provide an incremental solution. With libpreopen, you can create a list of file paths that the application legitimately needs access to, and then you can use open, but just with those file paths. So what's next? Well, we think that WASI core is a really good start. It preserves WebAssembly's portability and security, providing a solid foundation for an ecosystem. But there are still questions that we're going to need to answer as we develop this standard. So those questions include things like asynchronous I/O and file watching and file locking. We also need a really solid runtime implementing these foundations in the right way, something that can serve as the base for many applications and many hosts. For this, we have WASM+, which is what you saw in the demonstrations earlier. It's a standalone WebAssembly runtime, and it's intended to be very pluggable so that you can build custom-tailored hosts on top of it. We think it can be the best-in-class runtime for things from IoT devices all the way up to the cloud. And we're looking forward to talking to people who think that it can help with their use cases. So if you think it might help with something that you're working on, please come and find me. Happy to talk more about all of this. I want to say thank you to all of the people on the team who are driving these exciting developments, both with interface types and with WASI and WASM+. And I want to say thank you for listening.